Hey, what's up?
How are you?
Good. How are you doing?
I'm good.
So I was actually just trying to pull the questions up and I was having some trouble getting them up. So I just now did. So
It's totally fine. I was like, I had it in my head to do last night, and then I was working on my personal statement and totally had that leave my brain. So my
oh
bad. I
yeah,
will
no.
do better to send that much earlier.
Oh, you're totally
Um,
fine, and we'll probably still be able to get through them. Like I
yeah,
said,
yeah, yeah.
almost nobody ever succeeds in sending them to me on time. So it's
I'm
a bit
gonna try.
crazy.
I'm
So
really gonna try.
also, I don't know why I look really strange right now. I don't know if it looks really weird on your thing or not. I feel like I look like I'm a cartoon character or something right now. Do you see what is it showing up on yours? Okay, I just didn't want you to think that I was doing this on purpose. Because
Oh
on
no,
my
it's
end it
probably
looks
just
like
a internet connection thing.
yeah, I think it's some issue on my end
Yeah.
where it looks like my face is just like completely white except for just my eyes. And I just didn't want you to think that I'm like trying
Oh,
to do
you're
some
like a
weird camera
ghost or
effect.
something.
Yeah,
Okay.
exactly.
Um,
Anyway, so go
Also,
ahead.
one more thing, sorry. So somewhat of a long story, but Williams sent us this thing like on Friday of all these things we need to have due to them for applications today. I
Okay.
have them mostly done, but I really should probably go by 8:30 just to make sure I have them done and have some room for error if
Okay.
like something logistically goes wrong. So I'm gonna really try to be like if it's 8:40, it's fine, but I'm just gonna really try
Okay.
because I think most of the time I'll be much more flexible on the back end. But I was like, oh my God, like don't send us an email on Friday about like these 8 things we need to do.
Yeah, that
Um,
sucks. Yeah, no,
yeah.
that's is it for your med school application or
Yeah, it's
what's
for like the
okay.
committee. And it's nothing like big. It's just like this weird software and like none of us know how to do it. And I was like texting my friends at work all day and we are all trying to figure it out. I think we figured it out. I think it's fine. I think I only need like a little bit more time, but I'm just yeah. Anyways, that was my day.
Yeah.
So
Yeah,
sorry
better
about
safe
that.
than sorry. Oh yeah, no, you're
Yeah.
totally fine. Don't worry about it. I'm pulling up a couple things really
Yep.
quick and yeah, sorry. I meant to be able to go over these questions ahead of time. I
No,
just didn't get down
it's
here. I'm still at my parents' house,
yeah.
and so I was visiting with grandparents and stuff.
Oh,
So,
fun.
um, yeah. So normally if you send it, you gave me plenty of time today. I
Okay.
just didn't get it done. That's so my fault. But that won't normally happen. It's just an exceptional thing where like you kind of feel like you need to talk to parents and grandparents and stuff whenever.
Oh, uh-huh. Yeah,
Yeah.
as you
So
should. 100%.
and okay, so I'm sharing my screen now.
Well,
And if you want, we can just start on the first question.
yeah, I think it
Of
was like a torque one.
yeah,
It was like
I
a
feel like
astrophysics something or other, and I was like, "What is happening?"
yeah, talking about black holes. It looks like.
It was like the first question I opened on a Saturday morning. I was like, "This is not what I need." Torque and black holes. It's like, "What?" Like,
Yeah, understandable. Okay, so I'm just gonna just skim through this really quick,
yeah,
and
yeah, take your time.
it might actually be worth us doing this simultaneously. Sorry, I just realized that was
Yeah,
where I can jump.
probably.
Because reading passages is one of the strategy things that you and I will spend a lot of time going over at some point.
Okay,
So now wouldn't be the worst time to do this. So yeah, so, kind of killing two birds with one stone. So
perfect.
first thing to note whenever you're looking at science passages on the MCAT is what sort of what category the passage falls under. And by that I mean, is it an experimental passage or or an informational passage? Because they'll
Yes.
almost always read as one of those two, either experimental or uh, informational. So informational be meaning like a textbook, and experimental being more like just walking you through an experiment that was done somewhat like a scientific paper. Frequently those will have graphs and stuff. This is actually a really rare passage in as I'm looking at it right now, in that it doesn't have any real images. I mean, it has these equations, but no images. So anytime
Yeah.
you run into like a graph or an image or a figure or anything on the MCAT, you want to pay particular attention to that, because as of last I heard, which was about a year ago, there's still never been a passage on the MCAT that has a figure that doesn't actually have a question about it. And so those are likely to be very question
Yeah.
centric components of the passage. So just FYI.
Okay.
Okay, so if you don't if it's cool with you, we might just go through this passage together. We won't always do this unless you
Yeah,
want
let's
to,
do it.
but just to talk about kind of what to think about. So informational passages, which is what this one is almost definitely going to be. You can kind of just tell by the fact that there aren't lots of complicated graphs and figures, and they're not talking about an experiment that was done or doesn't look like it right off the bat. So you can generally read these a little bit faster than you can read the experimental passages. Those take a lot more diving into and a lot more specific stuff. So when we hit one of those, we can talk about what to do in that instance. Okay, cool. So take a breath. All right. So yeah. So all right, black holes have so I'll just start out. Black holes have played an important part in astrophysics for the last half century. Black holes are a region of space where the force of gravity is especially strong, and gravitational potential energy, U, is very large, obviously. Analogous to electrostatic potential energy associated with electrical charges, U is defined as the work required to move an object of mass m an infinite distance to a point at radial distance r within the gravitational field of a second mass big M, as given by this equation. So this is something like right off the bat, this is something you should be relatively familiar with by test day, because it does look exactly like the equation for electrostatics.
Yes.
Yeah, right. Okay. So all right. So really nothing new in this first paragraph so far. All right.
They're just making electrostatics like instead of like small charges, it's big black hole.
Yeah, exactly. Okay. So in electrostatics, when they do this, you've got like this will be like big Q versus, and this will be like little q, right?
Yeah.
So it's going to be identical to that, really. Okay. So and obviously like this joules, right? Because it's energy. Okay. So it's saying where big G is the gravitational constant near a black hole, the gravitational potential energy can become so negative that not even light has enough energy to escape the black hole's gravity, which is interesting. Okay, so escape velocity can be determined by launching an object of mass little m with velocity v to an infinite radial distance from the surface of central mass big M. I'm just making sure. Okay, from the surface of a central mass big M star or planet with radius big R. For a black hole to exist, the escape velocity must be equal to the speed of light. Okay, cool. So what are they saying with that paragraph? Because that's actually kind of a dense paragraph. Like, what's the point there?
That you have to have certain variables have to be a certain value in order to escape the black hole.
Right. Okay. Yeah, more or less. So, okay. So what more specifically though? Because they're being very specific about one thing here. So like if you had to write a sort of maybe, okay, I'll back up just a little bit. I should have said this right off the top, my bad. But so whenever you're going through these passages, especially in an informational passage, you want to kind of like, I don't want you to have to like write down, this is sort of modified from the Kaplan strategy. But so what Kaplan has people do is you'll write like paragraph 1, paragraph 2, paragraph 3, paragraph 4 on some scratch paper as you're reading these. And then you'll sort of like summarize each paragraph along the way. And I found that to be not that useful because it's extremely time consuming.
Yeah.
So what I've come up with is sort of a modified way of doing that, where rather than writing down like a summary of the paragraph, you've got the paragraph right in front of you. You don't need to write a summary of it. But what you should do instead though is write down, or at least think about, how does this paragraph change my perspective on this passage, or what is introduced in this paragraph that is new, or how is this paragraph likely to be pertinent to questions, right? So you don't always have to write something. Like for instance, if I was calling like this paragraph 1, this paragraph 2, 3, 4, maybe, then I wouldn't really write anything in paragraph 1 except maybe just like equation 1, because that's really all paragraph 1 is about. Yeah. But then paragraph 2 is saying something actually pretty interesting. So what is it that they're sort of like adding? What is paragraph 2 adding that wasn't really given to you in paragraph 1? Or how does that change your perspective on paragraph 1?
So that's the first time it mentions the escape velocity.
Okay.
And it's telling you how some object can escape a black hole.
Okay.
And for that object to escape, for the black hole to exist, the escape velocity must be the speed of light.
Right. For a black hole specifically. Because any celestial body, or really any mass at all, is going to have a certain escape velocity for another smaller mass to get away from it. Right.
Yeah.
So like Yeah, so in order for like Elon Musk to launch stuff into orbit, his rockets have to achieve a certain escape velocity to get outside the Earth's gravitational pull. I guess to launch stuff to Mars maybe is a better example. Like we have to get
Yeah.
outside the Earth's gravity in order to get to Mars.
So like
And so
if
with
there's
this,
something in the black hole, it has to be traveling fast enough essentially to counteract and then some the gravitational
yeah,
force.
precisely. Yeah,
Okay.
exactly. And so
Okay.
what this is saying is that in order for a black hole to exist, the escape velocity must be the speed of light. Right?
Yes.
Because if the escape velocity is lower than the speed of light, then light would be able to escape because light's moving fast enough to escape.
Yes.
So what it's telling you is that the black hole has to be so big, or the gravitational potential energy for the black hole has to be so negative, right? So great, because they just threw this little negative sign here that doesn't need to be there, but they decided to put it there. So it has to be,
Yeah.
it has to be so great that even something moving at the speed of light can't escape. And that's like
Yeah.
the definition of a black hole. Okay. So so you could say like escape velocity, and you can write whatever you want. You can write as much or as little as you want. This is something that I want you to kind of experiment with as you're doing these practice questions and practice
Yeah.
passages, because some people will like to write a lot, and that tends to be people who are faster readers, because they can afford it. Whereas
They
other
have some
people
time, yeah.
yeah, like, so for me, sometimes I won't write really anything at all, but I'll still have this structure there because I'll at least like quiz myself in my head at the end of each paragraph. Like, okay, what did this paragraph add? What did this paragraph change? How is
Yes.
this paragraph
Got it.
pertinent at all? Because sometimes you can just put like this paragraph is just about to the point where I would put a big X through it. Not because it doesn't have any information,
It
but it
just
has
says what
information
the
that I
equation
know.
says.
Right.
Yeah.
Yeah, exactly.
It's just
Exactly.
describing the equation. Yeah.
Perfect. And then whenever you go back to look at the paragraph or the passage to find answers to your questions, if you've got a giant X through one of the paragraphs, that's helpful because it narrows down your search basically. Okay, so so for a black hole, escape velocity equals, you could write speed of light. I'm just going to write c because e equals mc squared. Speed of light is c. Okay, so escape velocity equals c, and you can write whatever you want, as much or as little as possible. It's something that it's kind of an art, so it's something that you'll have to practice in order to.
I'll mess with it and see what I like best.
Right. Yeah. You want to just find out what works for you personally. The key is just to make yourself an active reader or an engaged reader, because it's easy to space out, start freaking out, and let your
on
mind
hour
run
8.
away.
Yeah, it's easy to.
Absolutely. Yeah, for sure. Okay. So next paragraph here. All right. So this says scientists have thoroughly studied the physics of black holes. Stars near the center of our galaxy have been observed to orbit an extremely massive, invisible object, billions of times more massive than our sun, that is almost certainly a black hole. The orbital angular velocity, whatever that is, I'm bad at Greek alphabet. I think it's omega, but of a star is defined as this. So it's like orbital angular velocity equals 360 degrees times little f, whatever little f is. All right, so I guess this isn't really paragraph 4. This is the same thing. All right, so then it says where little f is the frequency of rotation in hertz. All right, so how would you define little f? Like, try to put it in your own words for me, what little f is here.
How many times the mass, the star it like rotates per unit time, whatever the unit time they describe.
How often it rotates, or how often it?
Frequency of rotation.
Oh, does it say frequency of rotation? Oh, okay, gotcha.
Yeah.
My bad. Okay, yeah. So that's kind of weird because I was taking that to mean I may have misread it. I was taking that to mean that's how many times per second it goes around the black hole. So might be worth.
Oh, it says angular velocity of the star is defined as the. That's what I meant when I said rotation.
Oh, okay. Well,
orbit is probably better term.
Yeah, I like
but
the
I was
word
thinking
orbit,
that.
but they said rotation, so that's something that's not super clear to me. It might become clear in a second, but generally angular velocity means the velocity something's orbiting. Like angular velocity is that arrow as like the thing itself orbits the thing in the center. So that's why I'm taking it to be that. And
Well, like, I feel like rotating is like something like spinning around itself, not
yeah, that's
right?
why
Okay.
that's why the word rotation here is kind of weird to me. Right.
Rotation.
Yeah. Where F is the frequency of rotation. Maybe they're just misusing the word rotation. This is also
Well,
not
no, then
AM.
it says black holes are merely static mass, are not merely static masses, but are often observed to rotate about their own axes.
Yeah, so I guess we need to keep reading.
So I guess
All
our
right. Yeah.
interaction.
Okay, yeah. All right. I've always wondered about this. This is kind of interesting. Okay.
Black holes were made a fruitful area of research in the future. Like, okay,
Yeah, no kidding.
that's
Yeah.
fun.
Right. Yeah.
Thank you
Yeah.
for that fun fact that I
Yeah,
wasted time reading.
yeah,
Yeah.
that last sentence is literally totally waste of time. So, or the last two sentences. Yeah. Okay, cool. So, but powerful beams of ionized matter that project away from the black hole along the axis of rotation. Okay, so what's that maybe tell you? Because that's an interesting sentence.
So assuming the axis of rotation is in the middle, these pieces of ionized matter
Mm-hmm.
um, will come. So if the axis of rotation is in the middle, is that like theoretically what
Yeah, yeah.
it
It's
goes
like
like
if
straight out?
yeah, it's like if the
Okay.
black hole is like this thing and it's rotating, let's just say, it's like rotating this way, right? It's rotating so
Yeah.
that this is the axis of rotation,
So then it's
right?
going like,
Yeah, and if you ever have seen a picture of, like an artist's rendering of a black hole or something, it looks like this. They almost always look like this, where they have
oh,
these like
cool.
giant poles, like stuff shooting out of them at their poles. And I've always wondered what that was. So this is interesting.
So that's
Um,
saying that's the jet, which is the
yeah,
um, powerful beam of ionized matter.
yeah, and that's all we know right now. So
Sure.
yeah,
Okay.
yeah, and that's an important thing to note as well. Is like when you're reading an MCAT passage, almost never will you be completely aware of what's going on, and it's the more you can come to terms with that, the better.
Yeah.
Something I always tell people, because almost always students that I noticed that if students would just be a little bit more confident, that they might have an easier time with this test. And so
Okay.
I will try to, over the course of the next 6 weeks, I'm going to try to encourage you to err on the side of confidence a little bit.
Okay.
Not too much, because too much is stupid, but too much will hurt you. But
I don't know who's
I
too confident with the MCAT,
yeah,
but
no. Well, some people are, but those people aren't fun people to be around. Okay.
this is true. Yeah.
Right. Okay, so here we go. Let's look at so do you have like did you give a specific question, or was it just this passage in general?
It
I
was
think it was.
generally the passage. I think I wrote for all of those, I wrote down one question, but I
Okay,
meant
cool.
like the whole passage because I think
Okay.
my understanding wasn't great, even if I got some of them right.
Okay, cool. Yeah, I've got all the questions here. So we can just do
Fantastic.
every question if you want. Let's
Yeah, and if
see.
I'm like, okay, that's fine, we can just move on to the next one.
Right. Yeah. So all right, let me pull this in. Oh wait, that's not what I meant to do. So this is how I'll normally do this. Is when we're going through questions, I've got this little thing that lets me screenshot this out of here, so that way we can write on it.
Oh,
Um,
fun. Oh,
Unfortunately, it shows the answer next to it, but
well,
whatever.
that's okay.
Okay, cool.
I
So
theoretically already know the answer, so
right, I guess so. Yeah. Yeah. So it says a star orbiting a black hole in a clockwise direction begins to slowly spiral inward due to counterclockwise drag force. All right. When the star's radial distance from the black hole is 1 times 10 to the negative or 10 to the sixth, a drag force of 250 newtons acts perpendicular to the orbit of radius. What is the torque on the star? All right. So what's the first thing you do here?
the torque equation, I would say,
Okay. Yeah. So what's the torque
or
equation?
draw a picture.
Yeah, I would draw the picture first, probably.
Okay. So I would draw like that circle that we had,
Okay.
like with the
Yeah.
dot in the middle for the axis of rotation. Yep.
All right.
Mhm.
That's
It's the
close enough, I
exact
guess.
same drawing on my page. And then so then do the drag force as opposite of the centripetal force.
Okay. All right. Yeah. So which direction is the centripetal force?
Um, out, so like up.
Up? So the centripetal force is normally going to be
It
like
goes
this.
like
It's normally directly
Yeah,
perpendicular
I
to the direction of travel. Yeah.
because it's like it like pulls it in, right?
Right.
Like that's
Yeah.
why if
Yeah.
you have a car, like it's that video they show you with like the car on like the perfectly like sideways track thing.
Oh
You know what
yeah.
I'm talking
Yeah.
about? And
Exactly.
it like okay,
Mhm.
yeah, yeah, no, I did know that. I was just blanking.
Yeah. Yeah. So
Okay.
why is there a force on this though? Because let's assume for a second that the thing isn't spiraling inward. Okay. So let's say
Yes.
that's just maintaining this orbit just for a
Yeah.
second. So if it's maintaining an orbit, let's just say it's 40 meters per second. It's obviously way greater than that in this example, but I'm just
Yeah.
digressing briefly for a second. So why is there a force at all here if this is going as constant 40 meters per second speed around the black hole or whatever the center
Yeah.
mass is? Because
Gravity.
yeah, so gravity's responsible for the force, but if you think about Newton's laws, um I'm trying to remember his first or second law. It doesn't matter, but I think it's the first law. It's that anything in motion will stay in motion, or anything at rest will stay at rest unless acted
Yeah.
upon by a external force or a net
Mhm.
external force. And so here we're traveling at a constant speed, right? And so generally speaking, if you're traveling at a constant velocity, that means that there's no net force acting on the object. But here, that's not the case. We do have a net force acting, right? This centripetal force, we label it FC, is constantly acting on this thing. So how can you reconcile that if it's maintaining a constant like angular momentum?
As in, like, why is it there's still force acting on it if
Yeah,
it's not accelerating?
right.
I would say gravity again.
Well, it is still gravity, but I'm saying like, how is it able to maintain this constant angular velocity if there is a net force on it?
Oh, I see what you're saying. I don't know.
Okay, yeah, and so the reason is I was kind of like throwing little hints, but I would be surprised if anybody would ever pick up on it. So this is, we could say, like angular velocity. I kept referring to it as speed because if I were to have just said velocity, then that'd be wrong. And reason being that this net force is acting on the object, and it's causing the velocity to constantly change, because if you remember, velocity is a vector quantity. And so since it's a vector
Yeah,
quantity, so it has like
yeah.
a magnitude and a direction. And so while the magnitude remains the same,
The
that
direction
angular,
doesn't. Yeah.
right, exactly. And so that's why you think of it, that's why you're able to reconcile the net force and still have a constant angular velocity.
Yeah, that makes sense.
Yeah, I just
Um,
wanted to emphasize that briefly because that's like the simpler version of this same question. So you kind of have to understand that first before you really get a complete understanding of this question specifically.
yeah, no, okay, yeah, that makes sense.
Okay, cool. So let's go back to thinking about what's actually going on here.
Okay, yeah. So
All
then
right.
we're gonna go to the torque equation. Um,
Okay.
that I don't know off the top of my head.
Yeah, so it's torque is equal to the radius, which is just going to be in meters,
Mhm.
times the force, right?
Yep.
And then you'll often see times sine of theta. And so what is theta here?
90.
Huh?
90?
Okay, yeah, theta is 90 here. Yeah, for sure. So, right. So
Yeah.
so theta is this angle, which in this case is 90 degrees. And so we can kind of just forget about that sine theta here because sine of 90 degrees is 1. And so it's just like that. Right.
Yes.
Okay, cool. So that's what's going on there. All right. So back to the question. So the first thing to do whenever you're reading these questions is try to rephrase the question in your own words. And that's hard here because there's a lot, like there's a lot going on, which is
A lot of
great.
words, yes.
Yeah, which is why drawing this diagram out to begin with was the right strategy, because
Yeah.
you're trying to figure out, okay, what's the scenario actually asking me about? Because that's so much of the battle on this. All right. So we've got this diagram. All right. And so it says it's beginning to slowly spiral inward, right?
Yes.
So why is it spiraling inward?
Because it's the counterclockwise drag force, so like a friction force is opposing the angular velocity.
Okay, right. Yeah, exactly. Yep. Yeah, so it's saying counterclockwise. So it's telling you that like that is going like this way, right?
Yes.
Okay, cool. All right. So it's saying when the star's radial distance is 1 times, so like we could go ahead and say that I'm going to draw it going this way because we're assuming this is a perfect circle, which it clearly is not, but give me a break.
Yeah, we can imagine.
Right. Yeah. Yeah. Okay. So, and whenever I write this out, one thing that I'm going to do is it says 1 times 10 to the 6 kilometers. I'm just going to go ahead and convert it to meters when I'm writing that out. And therefore, that way I just don't have to worry about it again. And so I'll just say like 10 to the 9 meters. Okay.
Cool.
And then your drag force, it said, was 250 newtons, right?
Yep.
All right. Cool. And that's perpendicular to the orbit radius. So actually your drag force is going to be
negative,
curving around that thing. Yeah. Whatever. Here. We'll just know that it's going that way.
Yeah.
All right. Cool. So what is the torque on the star?
And you just multiply those together.
You multiply what together?
The 250 and the 10 to the 9th.
Okay. Right.
Because that's the radius times the drag force.
Yeah.
Okay.
And that's all.
Yeah.
I mean, I was spending time drawing this thing out because I think the better lesson here is then how to get a specific answer on this question, because this question itself isn't that bad, but knowing how all these forces are set up and how to apply everything here is a lot more complicated, I think, because torque questions are not super intuitive, in my opinion.
Yeah, it's also, I don't know, I feel like that was something we didn't cover a ton. Like we did it like very briefly at the end, so I think that's also part of my and then have never thought about it since. So I think it's conceptually difficult, and I also feel like I don't have a ton of practice with it.
Okay. Yeah. So if you want to do another, I guess we have more questions on this. So do you want to? Do you want to do the rest of these questions on this, or do you want me to give you another torque scenario? It might be worth just to do the rest of the questions on this.
Can we just do the rest of the questions? I'll see how I feel, and then it's not that complicated, but that's definitely one of the physics topics I don't feel great about.
Right. Let me pull this because for some reason it's only giving me that one question. So let me get how to get this up really quick. Sorry about that.
No worries.
UWorld can be kind of annoying sometimes. Let's see. I need to find maybe it'll let me create a test with this in it. Huh. Come on.
I can pull it up also.
Yeah, I guess it's you have it on your UWorld, right?
Yes.
I mean, obviously, because you were taking it. I think if I launch my faculty portal thing, it'll actually be the easier way to access this.
I can.
But yeah, if you can get it up too, that would be great.
Yeah, I have it. If you want me to share my screen.
Oh yeah, was this in your first test or your second test you took?
Second test.
The second
I took no. It was on I started one today that I haven't finished in tutor mode, but I accidentally did this one in tutor mode too.
Okay.
So I didn't mean to do that, and I just went through it and I didn't look at the answers till the end because I couldn't figure out if you could change it.
Oh yeah, I know what you're saying. Yeah, I'm not sure about that either. So
I tried to do this as accurately as possible, but it probably wasn't perfect.
Right. Yeah, I think the way you did it is probably good. Yeah, this thing's not working for me. So yeah, if you could pull it up, that'd be great. Sorry about that.
Okay, cool. I don't know how do I share my screen?
I think so it's the little, I think I have to stop doing mine first.
Oh yeah, I got it.
I think you're getting it to work.
Window.
And I'll try to get mine pulled up as well, just so it'll come up next time.
Sorry, I have to allow Google
weird.
Chrome
What just
to
happened?
record my screen.
All right. So which question do you want to work on right now? That's probably the better way for me to
Let me
ask that.
go do it. We do 2.
Yeah, yeah. So it's 2. I have
Oh,
this
actually,
one.
no, that one's fine.
Oh, okay.
That's
2's
you
fine.
just multiply 360 by the inverse. I think. Yeah.
Yeah.
I'm fine on that one. Usually that's just unit conversions.
Right. Yeah. Yeah.
And then let's see the next one. I'm fine on 3.
Okay.
We just did 4.
Mm-hmm.
Oh yeah, can we do 5 if possible? It's
Yeah,
the
sure.
402702.
Yeah. Yeah.
Matter
I've got them.
falling in a gravitational field.
Yeah. I've got
Oh,
them in the right order now as well, too.
fantastic.
So yeah. Yeah. So we're good.
Oh, you even have them up. Wow. Okay.
Yeah. All right. Here you go. So matter falling. Okay. Wait. Dang it. All right. Matter falling in a gravitational field of central mass can form a hot charged fluid. Matter falling in it. Sorry, I will end up rereading stuff a lot if I notice that I didn't really process it, because that's better than like. And this is something I'll harp on a lot is
Mhm.
most people, the vast majority of people, and this is from a book that I read about like test taking strategies and stuff. Most people will in a multiple choice test will read the question, and then they'll read the answer choices, and then they'll realize that they have no idea what the question was, and they'll go back and do that. And on average, people do that 2.5 times per every single question. And so just imagine like how much time you're going to have whenever you stop doing that. So, but it's
And
something you really
actually,
have.
yeah.
It's
Okay.
something
But
you
that's like
really have to train
practice.
yourself for.
Yeah.
Absolutely. Yeah. Yeah. And so, I do it all the time still. And I've been aware of this for like 10 years. So
Okay.
just,
Got it.
yeah.
Yeah.
So it's something you have to very intentionally practice, but no. Okay.
Yeah.
So, all right. Matter falling in the gravitational field of a central mass can form a hot charged fluid. So what's that's saying? That's basically like if there is a strong gravitational field, the matter will get really hot and it forms a charged fluid rather than like a solid or a liquid or something, right?
Yeah.
Okay, so it's just saying lots of energy makes hot charged fluid, aka plasma. All right, the fluid matter orbiting some stars radiates infrared light, but the matter orbiting a black hole emits X-rays. Which of the following explains this discrepancy? The matter orbiting black holes must. Okay, so before you even read the answer choices here, what are the differences between a star and a black hole? Like, what
The
are a few
type
differences?
of light. So the fluid orbiting some stars radiates infrared light, but the matter
Mhm.
orbiting black holes is X-rays. So it's the
Okay,
type of electromagnetic wave.
right. What's the difference between infrared and X-ray?
The difference between wavelength and
Mhm.
energy.
Yeah, absolutely. So,
Yeah,
which one has a shorter wavelength?
infrared.
Infrared has a longer wavelength.
X-ray has shorter wavelength, higher energy. Infrared is the reverse
Yep.
of that. Okay.
Yeah, yeah, absolutely. Because there's this inverse
I know the
relationship
spectrum. I'll
between.
just need to re-memorize it. But
Right.
yeah.
Yeah. Yeah. So all you have to know here is that there's this inverse relationship between wavelength and frequency, right? Because the
Mhm.
speed is always the speed of light. And so if you have a shorter wavelength, you have a greater frequency, and frequency is directly correlated with energy, right?
Yeah.
So, okay. So, the X-rays have higher energy, right?
Higher energy, so they have shorter wavelength.
Yeah, shorter wavelength, higher
Okay.
energy for the same. That's the same thing.
Yeah.
And all right, and this is telling you that matter orbiting the black hole emits X-rays, whereas matter orbiting the star emits infrared light. So it's just telling you that the light being emitted is a lot higher energy from the black hole than from the
Mhm.
star, right? Which kind of makes sense because the black hole is going to speed this stuff up more, right? It's
Yeah,
got a
so the
greater
black hole
gravitational force.
has higher energy.
Absolutely. Yeah. And so
Okay.
this is all without reading answer choices. Now that we've made
Yeah,
a
now
solid prediction, then we can go read answer choices. And that's a much better way of answering these questions, because then you automatically disqualify yourself from falling into the traps that you could fall into. Right? Because
yes.
the answer choices are made to be tempting. And so, Yeah.
Yeah. Okay, got it.
All right, cool. So then, yeah, so we just go look at these. A, the matter orbiting black holes must be hotter than matter orbiting stars. What do you think about that?
Possible.
True, not possible. Okay, yeah, that works for me. All right, so
Not B.
the colder than matter orbiting stars. Yeah, that's not going to be true.
Not C, because it's going to have higher energy.
Right.
But
D.
it specifies kinetic. Because it could also
Yeah,
be heat energy.
that makes sense. Yeah, that's fair. Right.
Okay.
Have lower kinetic energy than
Viscosity doesn't make much sense.
exhibit higher viscosity. Right. That doesn't make a
So
lot of sense.
we're between A and C. I think A.
I agree. And C can't be. So C says have lower kinetic energy than matter orbiting stars. You would just predict that matter, because it's saying matter falling in a gravitational field. So that kind of means like matter being sped up by the gravitational field.
So it is kinetic.
Yeah.
Yeah.
So I would say that A is the right answer here. I didn't put my thing in tutor mode, so I can't tell you if we're right or not. Unfortunately, I need to pull that up. But
it is right.
Okay, yeah. Cool. That works. All right. Oops. What did I just do? Oh, I told it to submit the thing. Okay, yeah, that's right. All right, next one. Is there a question 6 on this passage?
There is not.
Okay, cool. All right, so are you?
There is a question 6.
Oh, there is a question.
I think it's just plugging into the power equation. So I got that one. Yeah.
Nice. 10 to the 44 watts. That's a lot. That's wild.
It's like black hole level.
Yeah. Nice. Okay, cool. So how do you feel about that passage? Do you have any other questions or anything about?
Yeah, no, I feel fine. It was mainly the torque one.
The torque thing.
Yeah,
okay.
The rest, I got a couple of the other ones wrong, but I think I got like all of the other ones wrong. But I went back and now I understand them other than the torque one. I was just like, what? But now I get it better.
Okay, cool. The last thing I would ask you about torque, and if I'm doing this and you're like, let's just move on, please feel free to tell me that you feel good. And so the last thing to ask about the torque thing is I want to set up a torque problem that's even a little easier. It's just like a teeter-totter, right? So you've got some fulcrum and levers on each side. You've got something, let's just say we've got like 1 kilogram over here and I don't know, 10 kilograms, or let's say 11 to make our lives easy. So 11 kilograms over here. So that tells you that you've got a net force of 10, or we could say 100 newtons pushing down right here.
Yeah.
Right. Because, you've got 1 over here, which would be lifting up. So really it's like 110 down, but then 10 up. And so you get 100 newtons, right?
Yeah.
So, okay. So for that, the torque equation is going to tell you you've got just like your radius. Let's just say that it's 1 meter on both of these. So your torque equation tells you that force is just going to be, right, the radius, which is 1 meter, times your 100 Newton force. And so torque really, I guess, is energy. So the rotational energy there is going to be that 100 joules.
100. Yeah.
Right. So then what if I then say you have somebody comes in and starts pushing down on, let's say here, let me scroll over a little bit. They come in and they start just like leaning on this side over here, but they're leaning with this angle, right? So they've got this angle, and we'll say that this is, I don't know, 30 degrees, right? And that they are doing it, that they're pushing downward, but at that angle. You see what I'm saying? So they're pushing on it with a force of, I don't know, let's go with another 100 newtons. Okay. So now how would you reconcile that, or how would you think about that?
So it would be an additional downward force. So you'd find the Y component and then add that to the torque.
Okay, yeah. So so how do you find the Y component?
Give me 1 sec. We would need the length of the arm or whoever's pushing it.
Okay, yeah. Say they're just pushing right here in the same spot, so it's still that 1 meter radius.
Okay. So then because you can't do trig then because you don't have a length, right?
Oh, I see what you're saying. So you can do trig, and it's comes back to this like idea of multiplying the torque having that sign of theta in the equation, right? And so now we know
Yeah, but
that
you
this,
can't do like SOHCA, TOA, that thing, because you don't have the length of the side
right?
of
Yeah, I
the.
guess, yeah. So
Okay,
you need to,
that's
fair enough.
yeah.
Okay,
So
and this is
you
why I
have.
try not to make up problems too much because, that.
Oh, no. I just wanted to make sure I was understanding. So you can do RF sine 30.
Hmm.
So are we saying the radius is 1 meter again?
Right. Yeah. Yeah.
So then you do the radius times 100 times the sine of 30.
Right. Exactly. Perfect.
Okay.
Okay. Cool. I
And
just
then you
wanted to make
add
sure.
that torque to the 100 of the downward.
Yep,
Yeah.
precisely.
Okay, got it.
Absolutely. I just wanted to make sure that you were cool with the whole torque equation, like why sine is in that torque equation.
Yes,
Because
got it.
you
Yep.
had asked about torque, so I just wanted, and the question didn't the question didn't account for the sine, so I just
It
wanted
was
to
990. Okay,
just
cool.
to give a nod toward that to make sure that you're good on that. Okay, cool. So next
The next one was 403706. It was thin layer chromatography.
which passage was it?
Give me a sec.
Because since you gave me the test ID, I just have the whole passage up,
Yes.
or I mean the whole test.
Question 11.
Okay.
The I don't know what passage number that would be. It's
Right. No,
question
I've
7
got it.
through 12 on the test.
Yeah. I've got it. I've got it right here. I'm
Oh,
pulling
got
it
it.
in right
Oh,
now.
perfect. Thank you.
Oh yeah, no problem. Right. So let's paste it here. Is this it?
Yes.
Okay, cool. So it's, and again, I haven't read the passage, but I think we'll be fine. Okay. So it says, why was the optimization for the oxidation of compound 3 monitored by thin layer chromatography? The resulting TLC, thin layer chromatography, okay, plate given in the passage is used to determine. All right. So unfortunately, we have the answer. But so what would you do upon reading this question? Suppose you haven't read answer choices yet. What are they asking for here?
They're asking like why they use TLC to monitor the reaction. Like
Okay,
why
right,
was that the
right,
best method to go about finding the answer to the problem?
right.
Or to
Yeah,
the
yeah. And so really this is just asking you to consider like qualities of thin layer chromatography and what it's good for,
Yeah.
right? Okay, yeah. So so what do you know about thin layer chromatography? What are your
So not much before I read the answer to
okay.
the question. So from my understanding after reading the answers is that the more polar the compound is, the higher up it goes on the um, whatever vessel is used. I think it's like a piece of paper or something,
Yeah, yeah.
effectively. Um, so, and then they use different solvents, it looks like.
Hmm. Yeah, what would be the point of using different solvents?
Um, well, if the substance is more polar, it's going to dissolve better in a polar substance, so it's going to go up higher, maybe.
Right, exactly. Yeah, yeah.
Okay.
Nice. Okay, cool. So yeah, so basically this question is just asking you to like say, it's saying like why is thin, like what about thin layer chromatography is useful to this experiment. So this is unfortunately one that, like, having not read the passage, I'm not super well equipped to comment on, but I
Yes.
could we can read it really quick. Um
Um,
so
so it just tells you, like, effectively that all of this reaction happens and the desired product is compound 4, and then it can be over oxidized into compound 5.
okay.
And then they study different reaction conditions using different solvents, it looks like, to determine like how to get the optimal oxidation of compound 4, not compound 5.
Gotcha. Yeah. Okay. Yeah,
Okay,
so
yeah, no, I
then
think I get that.
yeah, yeah, you basically just explained the whole thing to me. Like that's why the answer is what the answer is because it's just trying to, so they're using thin layer chromatography as a means of determining like which scenario for this reaction is going to optimize for
Yes.
compound 3 basically. Yeah.
Um,
and none of the other answer choices are consistent with optimizing for compound 3, right? Like for instance, C is a good example here. Whether compound 4 or compound 5 is more polar. Who gives a shit? We're talking about compound 3. That, you know, like that's
Yes. Yeah.
Okay, cool.
Yeah, got it. Okay. There's one more question on this passage. Oh, that's not what I'm looking for. It's the Sn2 Stereochemistry.
Okay.
I think I understand it, but can we go over that like really fast?
Yeah, which question number is it, or do you
Oh,
just want to talk
sorry.
about SN2?
It's question 9. So it's 2 questions before that one we just did.
Okay. All right. Yeah. So
So can I
we
see if I explain it looking at the diagram and the answer?
yeah, absolutely. Go for it.
So then it's the nucleophile attacks at like the base where like the oxygen connects in the like triangle. I know that's not the right word, but it looks like a triangle.
I see what you're saying. Yeah.
And then when it attacks, that inverts the stereochemistry of it. So it like comes from like behind essentially and then
Mhm.
inverts the stereochemistry. And that's why the answer is B, because the stereochemistry of the rest is the same other than that one um like hydroxyl group where it's switched and that's where the nucleophile like attacked. Is that the idea?
Yeah, that's precisely correct. Yeah,
Okay,
that's
so it's
yeah.
just the one like so it attacks on that carbon. It's only the things attached to that carbon that flip, right?
Yeah. Yep.
Okay.
Mhm.
Okay, yeah.
Yeah,
Then I'm good.
exactly. Okay, so you're good with this
I just wanted to
SN2
make sure I
mechanism and stuff?
actually understood that because I like vaguely remembered learning that, but I haven't thought of that in a while.
Yeah. So
Yeah.
why is it, just to follow up, and again, you can opt out of the follow-up questions if you feel
No,
like
that's
you're
fine.
good on it. But why does the SN2 reaction lead to an inversion of stereochemistry? You said it. I just want to kind of drive it home.
'Cause like the nucleophile like comes from like behind, so it's least sterically hindered,
Okay.
right? So then when it like makes it like takes the place of the other one, essentially pushing the group back. Wait, no, that doesn't make sense because it's not taking the place. Um, seeing if it says it. It just says,
I can
therefore, the electrophilic carbon undergoes inversion of stereochemistry.
right. Okay. Yeah. So I can show you this if
Yeah.
you think that'd be helpful. Okay. So let's just draw out. Let me see here. Okay, let's just draw out a carbon with a bunch of stuff around it. I'm just gonna make these 1, 2, 3, and 4, if that's
Perfect.
okay. And we'll just say that
Yep.
they are in that order priority. All right.
Hmm.
Okay, so let's say that that 1 here is going to be our leaving group. Okay.
Yep.
Which is frequently the case because normally your leaving group is something that is a high priority atom, right? Bromine or
Yes.
something like that. Okay.
Yeah.
Right. And so if we have this stereochemistry right now where we've got 1, 2, 3, what is this R or S around this carbon right now?
I'm trying to remember the difference. One is
I can
clockwise,
tell you.
one is one is
Yeah.
clockwise, one is counterclockwise. R
Yeah.
is clockwise.
Correct. R is
Okay.
clockwise. Yeah.
Okay.
Yeah. And S stands for sinister. And so, like that, I don't know if sinister means left to you, but for a lot of people it does. And so, if you're left-handed, you might take offense to that. But
Got it. Easy way to
yeah, but
remember that.
yeah,
Okay.
it's a way to remember it. Yeah, for sure. So this is S right now because of that. You were saying R is clockwise. I didn't mean that. So
Yeah.
like,
No.
yeah,
So S is because it's counterclockwise. Yeah.
yeah. S is
Yeah.
counterclockwise, so that's S right now. Okay, cool. So whenever the nucleophile comes in, so we'll just have our nucleophile right here. It's
Hmm.
going to come in right with its electrons and going to attack the carbon. And the key thing here is that it's going to attack on the opposite side of the leaving group. All right. So here I
Yes.
have my two sticks here. 1 and 2 are in the plane of the page, right? And then 3 is out in front of the page and 4 is behind the page. Okay.
Yeah.
And so the reason I put 1 in the plane of the page is so I can keep the nucleophile also in the plane of the page. It just makes it a little bit simpler to think about.
Yeah.
Okay. So once the nucleophile attacks, this all happens sort of in one step, but there's this strange intermediate that is unique to the Sn2 reaction that has 5 groups around the carbon. Okay, so I wouldn't call it an intermediate. I call it the transition state. That's more accurate.
Yeah.
We talked about transition states the other day. This is the Sn2 transition state. And so the transition state is going to look like this. You've got your carbon, right? And then you still have your leaving group that's in the plane of the page. And you still have the number 2 thing, which is also in the plane of the page, but it's moved up a little bit. And the reason it's moved up is because you also now have this nucleophile also in the plane of the page, just on the opposite side from the leaving group.
Yeah.
And then in the same plane as this 2, but not in the plane of the page. So if you imagine you've got your page, and then perpendicular to your page, you have another plane.
Mm-hmm.
See what I'm saying? So
Yeah.
and in that plane is where 3 and 4 are going to sit. But 3 is coming out from the page, and 4 is back behind the page. But so you've got 2 different planes being formed. You have your one plane with 1, 2, and nucleophile, and then you have another plane with 2, 3, and 4. So those are your 2 planes that are like crossing each other. All right, I'm gonna make those lines go away because that makes it confusing. All right, so obviously this thing's hyper unstable. So what's going to happen is your leaving group's going to head out, right?
Yep.
Now that the nucleophile is attacked. And we're going to be left with, well, now that the leaving group is left, 2 came from below, right, over here on the left side. But now that the nucleophile came from the other side, it's just going to, 2's going to go ahead and just fill in the empty space left by 1. So you've got your carbon still. And now you've got 2 is kind of up in this direction, just like it basically 90 degrees from where it was prior over here.
Because it's all just like gonna like shift essentially.
Right, exactly. And so
Yeah.
your nucleophile is right where the leaving group was, just completely inverted, right? Because it came from the
Mhm.
bottom where the leaving group left on top.
I see.
And then,
Yeah.
yeah. And so then you've still got your wedge for 3 and your dashes for 4, right? But the whole thing is basically just flipped over from the starting
Yeah.
molecule.
So the
And I didn't do a good
nucleophile is
job
just
drawing.
taking the place of the leaving group on
Yeah,
the
but
other side of the molecule.
right, but it does
Yeah.
so from the other side of the molecule. So
Yeah.
now if you look at this, because again, the nucleophile is going to be a lot like the leaving group, it's probably going to be the highest priority thing, right? So if we say this is priority 1, right? So you've got 1, 2, 3. Well, is this R or S now?
Now it is clockwise, so R.
Right, exactly. So it was counterclockwise S before, and now that it's clockwise, it becomes R. So that is inversion of stereochemistry.
Yes.
Right. Okay.
Got it.
And so that's what an Sn2 reaction does. That doesn't mean that the Sn2 reaction will always cause R to flip to S, right? Because sometimes you could get inversion of stereochemistry, but if, say, for instance, 2 is if the leaving group was the highest priority, but then the nucleophile is a lower priority than 2, than the second thing, then see how we
The
inverted
second
the whole
thing
molecule.
Yeah,
Right.
the second would take that place as opposed to the nucleophile, right?
Right. Well, so the second thing, it still looks exactly like it does here, but if 2 here is higher priority than nucleophile, then we rotate this direction.
Yeah. Yeah, got it. Yeah.
Okay. Yeah. Because that's probably how that's going to show up on the test, just because that's the hardest way they can make it. You get inversion of stereochemistry, but you still have R as your configuration because you swapped your priorities.
Yes, I got it.
Okay. Yeah. So that's like the double switch or whatever. It's kind of a BS question, but or not. I mean, it's really not, because if you understand it, you can get the answer. And most people will miss that still. Okay. So does that make sense?
Yes, that's good. Thank you.
Oh yeah, no problem. All right. So next thing, I guess.
The next one I had was the question number was 402536. I'll find the passage.
Yeah, I'm looking for it. 5. You said 536?
Yes, 40253. Okay.
Yeah, so it is about carboxylic acid derivatives.
Yeah.
That is the shortest passage I've ever seen in my life.
Yeah, and there was like 5 questions on it.
Wow, that's nice. Does that happen on?
I know, that means. Yeah, I was gonna agree with you.
Oh, okay.
Yeah,
All right,
I think my biggest issue here is that I just don't know the derivatives of carboxylic acids. And like I think my questions for you was like, is that something I like really need to know for the test? Because I know it's on my
Mhm.
study guide and I know roughly how it works, but I can't replicate it. So that is
Yeah,
something that is very important to know.
yeah. I would
Okay.
definitely know that. We could just talk about that in general really quick if you want,
Yeah,
and
that'd
then
be
you
great.
can
And
look back
then
at the question.
cool. Yeah.
Okay, cool. So the general carboxylic acid backbone is this. You've got R, right? It's just like the
Hmm.
rest of the molecule. Okay. And so then you've got your carbonyl carbon with its double bonded oxygen,
Yeah.
and then the other oxygen, and then the H, obviously. And so that
Hmm.
is your general carboxylic acid backbone. And so all the carboxylic acid derivatives are just going to be variations on this theme, right? So we'll just say this is the actual carboxylic acid. So one of the derivatives, for instance, is an ester. All right. So the ester is just O and then another R group rather than that
Hmm.
H, right? So ester is one carboxylic acid derivative. Do you know any others? Feel free to like give me
Oh, is an
directions.
alcohol?
Alcohol wouldn't be one because it's not going to have that double bonded O. So these are all going to be things that have like a
Yeah.
carbonyl and then another atom next to it. Like if it's a ketone,
Like
right?
a
If we
ketone.
just say that
Yeah.
this is just like a carbon, that doesn't work. That's not a carboxylic acid derivative. It has to be the other bounded thing, right? Because you've got R, then carbonyl carbon with
Hmm.
its carbonyl on it. So then you've got one other space here, and whatever this question mark is, as long as it's not a hydrogen, because then it would just be an aldehyde, right?
Hmm.
Or it's not a carbon, because then it would just be a
And it's a
ketone.
ketone.
But so as long as it's not a hydrogen, not a carbon, then it's a carboxylic acid derivative.
Okay.
Right. So what are some other things question mark could be? Because we made question mark OR. That works. What about OH? It can't be OH, right? Because that's just
That's a
carboxylic acid.
carboxylic acid. Yeah.
Okay. Yeah. So what are some other things?
So could it be like O and then like more carbons after?
That's what this is. That's the OR. The ester.
I see. Yeah, yeah.
Yeah. See, this
Um,
R prime could just be, we'll just
could
say
be
equals
anything, any
more
other group that's not like
carbons.
a, yeah, got it.
Yeah.
Um, not aldehyde, not ketone.
Hmm. So just name an atom that's not carbon and not hydrogen. That's a good
Nitrogen.
way to start. Okay, nitrogen. That's a good one. Right. So if you
I
have
see.
nitrogen,
Okay.
yeah. Yeah. So if
I
you
was
have
thinking it
nitrogen,
has
you
to
can have
be oxygen, so it doesn't have to be oxygen and then something else.
no, it could
Okay,
be anything else. Yeah.
got it.
Yeah. So
Fantastic.
nitrogen, you can have it be like NH2, right? Or you could have it be N and then H and a carbon, right? So it could be
Hmm.
any number of things off of that nitrogen. Point being, if the nitrogen is attached to the carbonyl carbon, then it's an amide. So this is called an amide,
Yes.
right? Okay, cool. Right. So from there, so we've got an ester, we've got an amide. What's another atom that could be there?
Um, F.
Okay, sure. Yeah. And I'm just gonna put X because X generally just means any halogen, right? So
Yeah.
halogens meaning chloride, fluorine, fluoride, whatever, iodine, bromine,
Hmm.
whatever, all of those.
Yeah,
Okay,
those
so
guys.
X is any of those. So these are called acyl halides. All right. So the halide, right, comes from the word halogen. Okay.
Hmm.
So an acyl group is just the R bound to the carbon, right? So that's an acyl group. This
Yes.
equals acyl. And so it's an acyl halide because it's then a halide attached to an acyl group.
Attached to the, yeah.
Right. Okay. Cool. All right. So you got ester, amide, acyl halide. There is one more. One more. Trying to think through in my head to make sure. Yeah, there's just one more. Okay. It took me a second. So the other one you're not gonna guess because it's just absurd.
Okay.
I'm just gonna give you this one. I'd
Okay,
be
thanks.
you can correct me if I'm wrong, but on this other one, so it's just here you've got an oxygen, right? Just like the ester, just like the
Hmm.
carboxylic acid, but then bound to that oxygen. So if I just drew this, like if it were just like CH3 or something, that would be an ester, right? So it can't be that.
Yes.
So bound to that oxygen, what we have is another carboxylic acid backbone. So it looks like that.
Mhm.
So you've got carbonyl, oxygen, carbonyl, right? And so this is called an anhydride. These are pretty uncommon, but they
Mhm.
are fair game for the MCAT. So I have to tell you
Okay.
about it. Yeah.
Cool. Got it.
All right, cool. So there are a lot of things you need to know about these carboxylic acid derivatives, and it's just 5 of these. But the most important thing to understand right off the bat is which ones are more stable and which ones are more reactive. Okay.
Got it.
So any thoughts on, because you can predict this with stuff you know, but it can be a little bit complicated. So which one would you guess is like the most reactive or most stable?
I would say
You can
the
pick one.
acyl halide because they're leaving groups.
Yeah, nice. Okay, perfect. Exactly.
Okay.
100%. So how do you know, how can you predict if something's a good leaving group or not? You're right. It is the most reactive.
The honest answer is that I've done a lot of organic chemistry problems, and in my years in college, and at some point I did know the reasoning as to why that is the case, but at this point, I just, like, know that when I look at a molecule, realistically, what is likely the most leaving group, the best leaving group.
Okay. Right. I'm writing here except not F, because if X is F here, then that is not good, right?
Yeah.
Because fluoride is not a good leaving group. Reason being because it's super electronegative and therefore extremely reactive. So whether
Yes.
something's a good leaving group or not depends on whether it's going to be chill by itself in solution,
Yes.
right? So like chloride is a pretty big molecule. It's somewhat electronegative, and so but because it's really big, a big atom, it's able to delocalize that single negative charge over the span of the entire
Like the
surface area of a
yeah.
bigger atom. Right.
Okay.
Whereas fluoride is similarly electronegative. It's more electronegative, but because it's way smaller, it's not able to delocalize that negative charge as well. And so it's not a good leaving group. But the rest of the
Yes. Got it.
halogens are. Okay, cool. So which one would you predict is the next most reactive? And use the exact same thing you used before. Like which of these are going to be cool by themselves?
I would say carboxylic acid or amide.
Okay, so the amide is going to be the most stable. We'll talk about that in a second because that's the most complicated situation. All right,
Okay.
so that's the least reactive. It's the worst leaving group. One reason why is because nitrogens, generally speaking, aren't really good at hanging on to just like a negative charge on their own. Because for each of these leaving groups, you have to think about how good is it at holding on to a
Yeah.
negative formal charge. And nitrogen is worse at that than oxygen, right?
Okay.
So the rest of these are going to be more reactive than that one because nitrogen is just the worst for hanging on to a negative charge. Oxygen is more electronegative, therefore better able to hold on to a negative charge.
Okay.
And so like that's part of the reason, but the bigger reason is, we'll talk about it in a second because it's way more complicated. The bigger reason, and you do have to know it. So, all right. So aside from that, between the carboxylic acid, the ester, and the anhydride, which of these, because the leaving groups are going to be this, and this, right? So which is going to be the best leaving group?
Is the anhydride more stable because it has resonance?
More
I
stable?
guess they
You
all
mean
do.
like
Just
is the
kidding.
molecule more stable or is the leaving group more stable?
Molecule.
Uh, it doesn't really have the ability to have resonance while it has, well, I guess it kind of does, but the resonance isn't very good while it
Is it
has,
really? It's gonna yeah, no, that's yeah.
while it's bound like this, the resonance isn't great.
Yeah.
However, so imagine this situation because you're onto something
But
when you
if
mention
that's the
resonance.
leaving group, then it
hmm
does. Yeah.
Yeah,
Okay.
yeah, because if it's the leaving group, then these electrons are just jumping onto that oxygen, right?
Mhm.
And so we're left with the acyl thing, the same thing that you would have if the halide left, which is what leaves it
Yes.
open to nucleophilic attack, right? You
Yes.
have some nucleophile that'll come in and attack, so those electrons leave. And so here's your leaving group. It's basically just the conjugate base of a carboxylic acid, right?
Yeah.
And carboxylic acids are acids, because they're able to drop off that proton. So it's the same
Yeah.
thing. So that's why this is stable, because you've got resonance here
You've
in the leaving
resonance
within.
there, but in the molecule itself, there really isn't because that there's like probably a tiny little fraction that would be.
Precisely. Yeah.
Yeah,
That's
okay.
yeah, perfect. You're thinking about it perfectly. Yeah. Okay, cool. So nice. All right. So then what about between the carboxylic acid and the ester? This is the most trivial one because obviously like those are really similar. They both got the oxygen that's going to have to take on the negative charge, right? So
Yeah,
then the
probably the
question,
ester because
the ester is more stable or less stable?
is more stable.
Okay. So
No,
the
less stable because the R could be something that is going to be something that isn't hydrogen, which is going to delocalize the negative charge better. So I guess that would be why the nucleophile is better, or the leaving group is better. Sorry.
yeah, so the leaving group of the carboxylic acid is actually better. Okay.
Okay.
So yeah, so the ester is
Why is
going to,
that?
yeah, that's a good question. So the reason is because that R has to be just like a carbon chain, right? If it was something else, like something that was able to delocalize the negative charge, then it would be an anhydride, right? So
Yeah.
yeah, and so
Yeah.
then you come down to the
Okay.
question of like we'll say like CH3, CH2, CH2. I'm just making a carbon chain OH
Mhm.
versus just HOH, right? And so the difference between those two, whenever we take this thing off and this thing off, or wait, sorry, other way around. Dang it, my bad. Whenever we take the proton off of each of those, the
Mhm.
difference between them is, well, they're both going to have that negative charge on the oxygen, but this long carbon chain is electron donating. And so since it's electron donating, it's actually going to make it the situation a little bit worse than if you just didn't have carbons there at all. Because the hydrogen is electron agnostic, right? So it just have this OH means that we
Mhm.
have like a full -1 formal charge. But because this other thing has this electron donation going on, so we've got like the CH, all these CHs. I don't know why I made that many, but then it's got the -1 formal charge still, and then a little bit more. So it's like,
Because of the okay. Yeah.
yeah. So you could say like formal charge of like -1.05 or something like that, right? Obviously I'm making
So
that
it's
up, but
slightly more negative, and that's going to be, yeah, slightly worse.
yeah, yeah.
Okay.
Yeah, so and so I'm saying negative like 1.05, or you could say like 1.1, or the
Yeah.
number doesn't matter. Just the point that it's more negative than just the single negative charge due to the electron donating effect. So that's why that is.
Yeah.
All right.
Okay.
So
Got it.
yeah, so if you have to put them in order just to rehash that, you would say that if we're going like stable to reactive, what's the order?
Um, will you scroll back up so I can?
Mm. I'm tempted to
Oh,
say
that's
no, but I'm
cheating.
doing it.
That's cheating.
No, I'll
The
do it.
halide one is the least stable. I'm not looking. And
Okay.
then it's
Okay.
the
I'll make.
anhydride,
Okay.
right?
Yeah. Yeah.
And
Yeah.
then um the carboxylic acid,
Okay. Nice.
and then the um ketone. No,
Ketone not an
not
option.
ketone, not an option. The OR, I forget what it's called.
Nice. Okay. Yeah, you're right. Ester.
Ester. Oh,
And last one.
oh, I'm missing one. What am I missing?
We barely discussed this one.
The NH, that's the
Nice.
I don't know the name, but that's the least, yeah,
Amide.
amide.
Yeah.
Because it's, yeah, nitrogen. Okay.
Gotcha. Yeah. Yeah. And so one last thing on this. I'm sorry, there's just so much here, but
No, no, don't worry about it.
this is the most important thing in organic chemistry on the MCAT is the
Yeah.
carboxylic acid derivative. So I just want to make sure
Okay.
that you have a good grip on this. So the last thing is this additional stability of the amide, because this is extremely important. And otherwise, this is gonna feel like I'm being super nitpicky, but I promise this is like extremely important for
Yeah,
all
no,
of
go
OChem
for
and
it.
biochem. Okay, cool. So all right, so you've got this carbonyl, right? And here's your nitrogen. And we'll just
Hmm.
say, I'm just going to put R2 here because it can be hydrogen, it can be carbons, it doesn't matter, right? Okay, so you've also got this lone pair on the nitrogen. Okay,
Mhm.
and this lone pair is able to form a resonance situation here where you've got these electrons jump up onto that oxygen. So you've got this resonance scenario where you have a small contributor to this structure of this thing has got this double bond between the carbon and the nitrogen. And
Yes.
obviously then it has a positive charge on it. So that looks like shit, right? But it is a, because it has the two formal charges on it. But there's enough of a contribution from this resonance structure that the carbon itself, this carbon right here, and this nitrogen are forced to take on an sp2 hybridization.
Yeah.
And so
I
that
have this on a
means,
flashcard. Yeah.
okay, cool. All right. Yeah. So
It took me
that
a
means,
second, but yes.
right. So what's that tell you about the geometry around those two atoms, around that
The
carbon and the nitrogen? But
the electrons can, like what you just said, delocalize and
okay,
form
yeah.
like the cloud, which is stabilizing.
It
So then
also
there's
though,
partial double bond character for both.
correct. Yeah. So partial
Okay.
double bond character. And that means that, well, the double bond's harder to break than a single bond, right?
Yeah.
So we'll call this like a 1.5 bond, sort of,
Yes.
right?
It's like the
Okay.
dotted
Yes.
line they always draw.
Yeah, exactly. So yeah,
Yeah,
if you
with the
wanted to
partial
draw
positive, partial negative.
right. Yeah.
Okay.
So you end up with this delocalization of these electrons so that so you have this situation where you've got this dotted line. Is that what you're talking about?
Mhm.
Sort of.
Yes.
All right. And so what that does also, in addition, is makes this thing stay sp2 hybridized, this nitrogen
Mhm.
hybridized. All right. And so what that does is it forces it to exist in a plane. Okay. So it means, right, because if it's sp2 hybridized, that means it only has three things around it. So it's not going to take on
Mhm.
that tetrahedral configuration. So it exists in a flat plane. So now we've got this is in a plane and this is in a plane. So the whole thing is forced to be in a singular plane. Okay. And that sounds trivial, but that plays a massive role in protein formation because if you think about it, when a protein forms, it's formed out of what? What are the constituent, the subunits
Amino
of a protein?
acids.
Okay, right.
Amino
Amino
acids.
acids. Amino acids look like this, right? You've got
They
your
all have the
N,
NH. Yeah.
right? So you've got your N, your central carbon, you've got some R group hydrogen, and this carbonyl or this carboxylic acid, right? But whenever
Mhm.
these things link together, they're going to bind with another N, right? So you've got this central carbon, H, R, and again, your other carboxylic acid. So when this bond happens, what we do is eliminate that oxygen. And so this
Mhm.
carbon binds to that nitrogen. And so because this is now an amide, right? It forces this whole part of the molecule to exist in one plane. And so it confers this certain rigidity to the protein that limits the possible number of configurations that the protein could take on. And it's actually like, if it wasn't for this, then there would be no life. And so that's how substantial this is.
Little important. Yeah.
Yeah, it's somewhat
Um.
important, right? Yeah,
Okay, so that just makes the protein chain then more stable because they're
exactly.
all in the same plane. Okay.
Right. And it also is responsible for, how protein secondary structures are alpha helices and beta
Mhm.
pleated sheets. This is responsible for the alpha helix formation. Because otherwise it would just, because the alpha helix is going to be, it's going to form something kind of like this. And you're going to have like 3.5 amino acids per turn. And the reason that you have to have 3.5 amino acids per turn is that you can only turn so much due to this plane. If you didn't have this,
I see.
yeah, if you didn't have that necessary plane, then you could have like 1 amino acid per turn. And so it'd just be this squiggly thing.
So it keeps
It's
it in the uniform because okay,
right, exactly. Yeah.
got it.
Yeah.
Cool.
And
Okay,
so
yeah, I
that's
didn't know that.
hugely important for, all of biology.
Yeah.
Yeah. Yeah. And also, if you think about the 1.5 bond, the partial double bond character that we were talking about,
Mhm.
that's very important for making peptide bonds just a little bit stronger than your typical single bond.
Yes. Yeah.
Also, one last thing, sorry. It also means that you can't rotate around a peptide bond
Yes.
because
So
it's
there
a
you can't
partial
have
double
any
bond.
of the I'm gonna call it spinning, but I know that's not what it's
No,
actually
that
called.
works. I
With
don't
the
care.
projection diagrams
Right.
that make my brain hurt around a single bond. Yeah.
Right. Yeah. So you can't have any rotation around that single bond, and so that also adds to the stability of a protein conformation. Yeah. So all this is
Because
really
even though
important.
when we draw it out, it like looks like a single bond, like there is that double bond character.
Right. Yeah. Even though it looks
Okay.
like a single bond, you have to know that you can't rotate around that bond. You can
Yeah.
rotate around some bonds in a protein, right? Because you can still rotate around this one, and you can still rotate around this one,
Yes, but
but
you
you can
can't rotate
actually.
around the one that connects the amino acids.
Right. Right. Exactly. So you can rotate within amino acids, but not between amino acids.
Yes.
Okay, cool. So that's very important to just like the nature of proteins, like super important. So just so you're aware. All
Yeah,
right.
got it.
Yeah. So you kind of see how what I'm saying whenever I'm like really I'm telling you I'm gonna very much emphasize integrating all of this to like
Yes.
one body of knowledge. And that's what this test really, really rewards. So just FYI.
Got it.
Yeah, the integration of everything. That's the most important part. The whole thing is the most important part. What a profound
For
statement.
every single question.
Yeah. Yeah, exactly. All right.
Okay, I'm
So
trying to see these
next thing.
questions if there's Can we go over question 23?
I think that's what we just did, right?
Um,
It's 23 on mine, the one we just talked. I guess we never actually addressed the question. We just talked
yeah,
about
it's the acid
all the derivatives.
catalyst. We just did the
Okay.
derivatives, yeah. The acid catalyst. So this is the esterification.
Okay.
So
Yeah, 1 second. Let me question.
23. Yeah.
Yeah, that's okay, cool. So this is if the carboxylic acid derivative that formed in the passage is reacted with an excess of 3-methyl butane 1 all, okay, and an acid catalyst, which of the following compounds will be the product? All right, cool. So carboxylic acid derivative that formed in the passage. So what does that look like?
So they reacted hexanoic acid and ethanol.
Oh, okay. Yeah, so what does hexanoic acid look like? Well, you got to have 1 carbon, 2 carbons, 3, 4, 5 carbons, 6. All right. So
And
that's
then
hexanoic acid right there. And they reacted it with what?
ethanol.
Okay. So if you have hexanoic acid and ethanol, right, that means you've got this ethyl group, ethanol, and I'm guessing, I haven't read the thing, ethanol in concentrated sulfuric acid. Okay. So it's just
Yeah, so
saying,
they're
yes. Yeah. So let's think about what that mechanism actually is.
so the so is it's in an acid.
Mm-hmm. Yeah. So how's that matter? It definitely matters.
Yeah, so the acid wants to take electrons, right?
That's a good question. That the Lewis definition is always difficult. Yeah, you're right though.
It
Yeah,
has too
yeah.
many hydrogens and wants to get rid of hydrogens. Is that
Right. Yeah, that's the other way to think. The
okay?
Bronsted-Lowry definition,
Yeah.
just
I
a
like that
little
one
easier.
better too.
Yeah, yeah. But the Lewis one is really good. You know, it's good to be aware of. And you said it
So
correctly. So
so
nice.
it
Gold
wants
star.
to get rid of hydrogens.
Yeah, the acid
So
does. Correct.
the acid wants, so it's in an acid, so it's going to so does it take the oxygen or does it take the hydroxyl group and make water?
That's a good thought. It doesn't do that, but it's a good thought. So water is going to form here. All right. But the first thing that's going to happen whenever you have that acid here
Mhm.
with a carboxylic acid derivative, if you have an acid present, like an acid catalyst like sulfuric acid, is the electrons on the carbonyl oxygen. So like this oxygen here, pick up a proton from the acid. So the first step is just that strange step that just looks like this. And so now we've just got this oxygen now has that hydrogen on it. It still has its double bond kind of, right? But now it's got this charge here. Okay.
Yeah.
So now that you have that situation, basically what we've created is a scenario where we've basically just like encouraged these double bond electrons to jump up here so that oxygen doesn't have to be positively charged anymore.
Yes.
Yeah, and so what that effectively does is it makes this carbon a lot more nucleophilic because now it's got like a partial carbocation character to it.
Yes.
Because when those electrons jump up to the oxygen, it's left with a positive charge on the carbon.
A positive charge, then it's going to want the nucleophile. So then the nucleophile is going to attack the carbonyl.
Yeah. So what this all does is it makes it so that something like ethanol that is otherwise a really bad nucleophile becomes a decent nucleophile. So now,
so the acid is just it's the catalyst, as it says.
Yeah, exactly.
Got it.
So now the oxygen on the ethanol comes in and attacks the carbonyl carbon. Okay.
And then the electrons pop up.
Right, exactly. Yeah, and so those electrons pop up onto that oxygen. So then what you're left with is, wish I hadn't committed to drawing the hexanoic acid thing. All right, so you've got this OH up here, right? Because its electrons jumped onto it. And then you've got this other OH that we already had, right? This one.
Yeah.
And then you've got the ethanol. I'm just going to keep writing ET. Okay, so now that's positively charged. Okay, this is a mess. This molecule is a complete mess. So what happens next? Well, this thing right here, this part of it where you get your carbonyl carbon and 4 things around it is called a tetrahedral intermediate. And this happens in all interconversions between carboxylic acid derivatives. You always end up with this tetrahedral intermediate once the nucleophile has attacked the carbonyl carbon. So you get this, but it's really unstable. And so what happens is something's got to leave so that we can reestablish the carbonyl group, right? So one of these has to head out, okay? And when it does, it's going to take the proton from the other one, right? So we'll say that this one's leaving, right? Its electrons jump onto it, okay?
Yep.
So that means you've got...
The proton pops off.
Yeah, so when those electrons jump onto it, these electrons from this one jump back down and reform that double bond, okay? So then we're left with this thing where now we've reformed our double bond, so we've still got our O and H, and this is positively charged, right? And then we have the O and the H here, ET, right? So that's positively charged. And this OH that left, right? Or this thing that left is going to pick up one of these protons, right? Because it just has to, you know, it's like that's a base, right? So you've got your OH.
And then that grabs the proton from the,
or the ethanol. You can pick either one. It doesn't matter because the next one's leaving in the next step. So so that happens. And then you're left with this again, 6 carbons. And now you've reformed your carbonyl. And then all that's still a mess is this part where you've just got this proton right there, right? And so the solvent is just going to come in and pick that up. And so this step right here, because remember, it's an acid catalyst, right? So when that leaves, we call this regeneration of the acid catalyst.
Yeah.
Because in order for something to be a catalyst, you have to reproduce it at the end of the reaction. It can't be used up. So this last step is just regeneration of the catalyst. And so what we're left with is this ester, right?
Yes.
And rather than the ET, I'll just go ahead and emphasize it maybe if it erases just like 2 more carbons, right? So that's the thing that we're left with after the part of the passage. And that doesn't even answer the question, right? Because the question is saying so. But it kind of does because so now carboxylic acid derivative, this thing, reacts with 3-methyl-butan-1-ol and an acid catalyst. So basically, we're going to do the same thing is what it's telling us.
Yes.
Right. Okay. So we basically just need to figure out what 3-methyl-butan-1-ol is. What do you think about that?
So it has methyl group on the third carbon? No.
I'm not saying you're wrong. No, I'm not saying you're wrong. You are right about that. That is correct. Yes, the methyl group on the third carbon. Okay. So how many carbons are there total?
4?
Yeah, 4 because of that root
The
word,
view,
butene.
yeah.
Yeah. Okay, so you've got 4 carbons. Well, 4 carbons in the main backbone, right?
Yeah. So then we have a methyl group off of the third carbon.
Okay, there you go. So we'll say that this is carbon 1, 2,
Yeah.
3, 4. There's your methyl.
And then it has a alcohol on the first,
Okay,
right?
so there's your OH.
Yeah.
All right, now what else? What have we not put in yet?
3 methyl.
Oh, wait, that's all. My bad.
Yeah, because then we have the 4, we have the alcohol, okay, yeah. So then that reacts the same way.
Mm-hmm. Yeah, so what
So
this is... Oh, go ahead. Go ahead.
effectively, the shortened way would be the ethanol of the example we did first is like the carbon chain. So
Right.
it added 2 carbons to the end, so we just have to add the 3-methyl butane to the
Yeah.
derivative in the box.
Yeah, exactly. So what you're
Okay.
gonna do is the same what this is called is a transesterification reaction because you're going
Yeah.
from one ester to a new one. And so basically this is your leaving group, right? Because that's
Yeah.
the part of the molecule that's gonna leave. And so this oxygen is gonna come in and attack right there.
Yeah.
Right. So what you're left with is gonna be something to this. I'll make it red so we can emphasize that it's important. So here's your parent molecule. Here's your carbonyl, right?
Mhm.
So this is your O, right? So that is that O. Then you've got your 1 carbon, 2 carbon, 3 carbon, and that's the one that has the methyl coming off of it.
Mhm.
And then that 4th thing. So that's what it looks like, probably.
Yeah.
Hope that matches an answer choice, please.
I think it does.
Yeah, it does. I just looked.
Cool.
Yeah, so that is, well, B. They kind of ruin it for us, but yeah, it's a
Yeah.
lot going on there. But there's a lot going on there, but it was very repetitive.
Yeah, if you did it once, you could do it again.
Right, exactly.
And I also think I wouldn't have to go through all those steps the next time, knowing how generally
Right.
that works. Yeah.
Yeah, I just wanted to give you like the full rundown of how that mechanism worked because now you
Yeah.
can just know that's what happens and shortcut it a little bit. But
Yeah.
if you have a good nucleophile present, then you don't need an acid catalyst for this, just FYI.
Yeah, because the acid catalyst is what allows that to then become a good electrophile, the
Right.
portion of the molecule, yeah, that where the
Yeah.
nucleophile attacks. Okay.
Yeah, you could run this exact same reaction in extremely basic solution and it would also work.
Yes.
Right. Yeah, you just have like your base would have to be the nucleophile.
Yes. Got it.
Okay, cool. All right, nice. Next thing. Oh, no,
I think
also I
that
just
was
noticed it's 8:30 your time, right?
yeah, and I think that was my last, like, problem I wanted to go over, I think. Let me
Okay,
just make
cool.
sure. Yeah, I think I understand the rest of the answers I got wrong on this one.
Nice.
But yeah, so I'm gonna keep going through. I've done, I think, 70 practice problems thus far. So I'll try
Nice.
to get to that.
Awesome.
I think we had said like between 250 and 300 between now and when I see you on Friday.
Right. Yeah. Yeah. Absolutely. Yeah.
Yeah.
Absolutely.
And I'll
Yeah. Oh, go ahead.
I'll
Sorry.
just I'll just do the same thing and write down and actually send um the questions.
Okay. Yeah. Yeah. For
Yeah.
sure. Yeah. And just FYI, again, I know I already said this to you. I'm gonna keep saying it though. Is that like I can tell you're really smart. Okay. So like if to whatever extent you don't do as well as like as well as you want to do on this test, it's gonna
Yeah.
be you not preparing rather than you not having the tools to succeed.
Yeah. Yeah.
And that's not me being mean. Like that's actually me like just letting you know, hey, you have all the tools. So it's just a matter of doing it.
Prepare
Just FYI.
properly. Yeah.
Yeah,
That's the
yeah,
goal. That
yeah.
really is the goal. Um,
Yeah, no, I know. I mean, obviously you came and found me and
yes.
and we're doing this. So you're on the right track. I
Yeah.
just wanted to let you
Just
to encourage you like you could do as well as you want to do on this test. It's just going to be
yeah.
how much you want to put into it.
Yeah. That is really what I'm gonna try to do.
Cool.
I
Yeah.
had I had one more really quick question. So
Mhm.
I what I started doing this session, like, halfway through was not writing down and just listening and paying attention because I feel like I was, like, 1, slowing us down, and 2, not paying enough attention, like, just worrying about writing things down.
Yeah, yeah.
Do you have people that just go back and then write things down after? Do you think that's a waste of time?
Yeah, I think that that's probably the best way to do it is not to try to write down everything I say because I'm giving you the
Yeah.
video and I can also generate a transcript of everything I say if you want to go back and read it. Like that's easy for me to
I
do.
don't think that's
I can really
needed.
easily send you that. Okay. All right. But you'll have the video and you'll have all of the stuff that I wrote down too.
Yeah.
So yeah, you can do either
And then
one.
just go back, and I'm sure I can watch it on, like, 2 times speed or something if I want to.
Yeah, yeah, absolutely.
That
That's why I
could be an option.
host them all on YouTube. So you have the file in that folder for you
Mhm.
that you
Yes.
have, right? But I don't know. I just want to point this out just in case you hadn't seen it yet. That one second. Whenever I pull up, I'm opening your folder. So whenever I open this Excel sheet, that is your Excel sheet.
Mhm.
Why is that not updated? That's insane. My bad. Okay, it's updated now. Um, so so when this updates itself, I don't know why that was, because I had done it. Obviously, it's just updated. Uh, then whenever you go see where this column that has a video URL in it,
Mhm.
if you click on this link, which I don't know why it's not making itself clickable, link, just go to open
Can
it.
always copy and paste it.
Right, yeah, that's why I
No big
made
deal,
like a
yeah.
still though. Come on. Okay, here, I'll copy and paste it. Wait, what? Okay, I just screwed it up. Well, I thought this would be easier. Hang on a
All
second.
good,
Okay.
no
So see how there's
worries.
like a code in the thing? It's because
Yeah, yeah.
I use a master sheet that like lets me do this for everybody very easily. All right. Well, this is ridiculous. I'll fix
I'm
this.
guessing
Okay, there.
that just goes to a YouTube video and I can then
Right, exactly. Okay, yeah.
yeah,
So it goes
okay.
to a YouTube video and you can use all the stuff on YouTube, which, like
Fantastic.
you can run it at 2x and all of that business. I don't
Yeah.
know why that's not working. So let me know if that doesn't work and I'll fix it. I can also just
Okay,
send you
yeah.
the links. Yeah.
I think I need to finish my stuff to submit, and then I'll probably just do
Yeah,
practice problems tonight, so I don't think I'm gonna look at that video until probably tomorrow morning or tomorrow evening anyway, so no rush.
yeah, yeah, absolutely. I just wanted to make sure that you were aware that you could also watch them on YouTube or in the video files. There's a lot of redundancy here. So I just want to make it so
Perfect.
you can do it
Amazing.
any way you want. Yeah.
Okay, awesome. Thank you.
Yeah, yeah, no problem. But I'll go ahead and let you get going since I know you have stuff to do.
Oh, yeah, unfortunately.
Yeah. Also,
Figure
I
out
keep forgetting to mention this to you. Just if you know anybody else who could benefit from working with me or working with anybody that's working for me, just and you refer them to me, I will immediately Venmo you 10% of whatever they buy. Just
cool.
FYI. Yeah. So or we can
I'll
also
let you know.
yeah.
I have a
Yeah,
few
'cause
friends in the class below me that are graduating. One of my, like, best friends is graduating, in the spring and is gonna take the MCAT this summer, and she has a few other friends that I don't know quite as well, but I will be sure to let them know.
awesome. Yeah,
But
that'd be wonderful if you could do that. And
yeah,
I'm not
I
kidding.
think
Like
her
I'll
plan is to
legit
take it in the summer,
Okay, cool.
but she just got a concussion, so I don't know how that affects her, but
I hate that.
yeah,
Yeah.
oh, poor kid.
No,
Um,
that happens.
yeah.
Actually, I may already be working with this person that because I know a student who also came to me from Omar. So, yeah, but
That's funny. Cool.
anyway, yeah. Anyway,
Um,
but if you know anybody at all, and you send them my way, I will give you 10% because I'm trying to generate a client base, and
yeah, totally, as you should. Yeah, and I can also let my, thesis advisor know because she always has a lot of pre-med students,
awesome. Yeah, yeah, for
that
sure.
I'm sure she advises as well as she advised me.
Cool.
But
Yeah.
yeah, cool. Okay, awesome. Thank you
Awesome.
so much. I will see you, Thursday at 7:30.
Okay, perfect. Sounds great. I'll talk to
Yeah,
you then. Let me know if you have any
okay.
questions in between also.
Yeah, I
But
will. Thank you so much.
all right, yeah, no problem. Talk to you later.